say, picking right back up. I liked that. I liked having a shorter lecture. Maybe you enjoyed having a shorter lecture to watch as well. Let's keep it going. So in that last lecture, so we basically just talked about the Carnot cycle, and I introduced this Clausius inequality. Okay, this Clausius inequality is going to come back, so we'll see it. We'll see it relate, and you can see it's right there in front of you. And you notice on this learning goal with Carnot cycle, just be familiar, right? Don't write a PhD thesis on it. Just be familiar with the Carnot cycle and the thermodynamic efficiency and how that, I know it doesn't say it here, but how that led to the temperature scale, the Kelvin scale. Okay, so on this video, I'm just going to talk about two more learning goals. So know how to calculate entropy of various processes. So learning goal 8, and learning goal 9, know the third law of thermodynamics, and how to calculate third law entropies. Okay, and that's going to be a bigger activity that we do in your Igor. I don't know what the number of it's going to be. In your computer activity that I'm going to give you next week, it's going to be related to these types of calculations. Okay, folks? So let's get it going, all right? So entropy changes accompanying specific processes and how to calculate those. So we actually already talked about expansion, but I'll just give you a reminder. I'll give you a review on this. We know this starts with the thermodynamic definition of entropy, which says delta S equals the integral from initial to final conditions of dq reversible over temperature. And then obviously we've got to say, we've already said dq, right? So dq divided by t, okay? And so we know that reversible work will equal negative reversible heat, right? They're equal and opposite. Okay, and work supplied reversibly is negative nRT, natural log VF over VI, which means Q reversible is positive nRT, natural log VF over VI, okay? And thus, when we plug this in, okay, and we take dq of that, and we integrate it, divided by t, then that leaves us with delta S for expansion is just nR divided by natural log of VF over VI, okay? And here you can see this plot. This is showing you in this reduced variable space, right? So on the x-axis, it's showing you the ratio of VF over VI. And on the y-axis, it's showing you delta S divided by nR. So really, you're just seeing the logarithmic relationship there, okay? And so, of course, that relationship, so this is just using the ideal gas situation, but when we use real gases, right, we get different curvatures, okay? And that's related to those heat capacity ratios, those gamma ratios. I don't really want to spend much other time talking about that other than just kind of reviewing how I can put together calculating, entropy of expansion based on the other equations that I know. Okay, folks? So that's really all that I'm going to say there, all right? So moving on, let's talk about phase transitions, okay? So we can come up with this equation. So we note that the thermodynamic definition of entropy, right, is this dq reversible divided by temperature, okay? But we also know that Q at constant pressure equals delta H, okay? So another definition, another mathematical equation for entropy, delta S, so I'll just write this generally, delta S is delta H divided by T at constant pressure, okay? And now this TRS, okay, that stands for phase transition. And so now specifically the entropy of a phase transition is the enthalpy of the phase transition divided by the temperature at which that phase transition happens. Okay? And so here is a graphical representation. Here's for water. And so what you can see here, entropy, so we, as a function of temperature, right? So we're going to have to come up with some way of calculating this line. And we will in the next slide. So this is, I'm just saying molar entropy of the solid as a function of temperature, molar entropy of the liquid, or molar entropy of the gas, okay? And so, but now you notice that it's a discontinuous function, right? So at the phase transition, there's this huge jump. Well, that is this value right here, okay? So for example, that delta S standard of fusion, it equals the delta H standard of fusion divided by the temperature at which that happens, okay? And in the case of water, you can see that that's 22 joules per mole per K. For going from a solid to liquid, you can see going from a liquid to a gas, it's much, much bigger, which is not that surprising because there are far more microstates to describe a gas than there are that describe a liquid or a solid. So it's to be expected that there is a much bigger entropy change associated with going from a liquid to a gas versus going from a solid to a liquid. Okay. What's also pretty cool is we can use this relationship to start to conceptually know when a phase transition will be exothermic or when will be endothermic. So I'll show you as an example. Come up with 2 examples of exothermic phase transitions and 2 examples of endothermic phase transitions based on this consideration of delta S. Okay, so let's write that again. I'm going to drop saying the TRS, and we just know delta S equals delta H divided by T. Okay, so for example, and you can pause it and think about this if you like. I'm just going to keep moving forward. Okay, so suppose we go from a solid to a liquid. Will that be exothermic or endothermic? Okay, well, what do we expect for delta S out of this process? Okay, well, we expect delta S going from a solid to a liquid should be greater than 0, right? A liquid is, if you will, more chaotic than a solid, so we know there is an increase in entropy in going from a solid to a liquid. And because in this case delta S is greater than 0, then that means, therefore, delta H for this process has to be greater than 0. And that makes good sense, right? To melt a solid into a liquid, you have to put heat in. That makes good sense, okay? And so, for example, if we think about now going from suppose a gas to a liquid, what happens to delta S? Okay, well, a gas has a lot of microstates. It's fairly chaotic. Okay, a liquid has less. So there is a decrease in entropy in going from a gas to a liquid. All right, correspondingly, there has to be a release of heat. So this is an exothermic phase transition going from a gas to a liquid. And we might not have been able to guess that right away, but when we use this relationship, delta S equals delta H divided by T, then you get the right answer every time, because I think it's fairly straightforward for us to remember our entropy from the Gen Chem days, right? When we go from a solid to a liquid, that's an increase in entropy. Another one, liquid going to a gas, that would be a positive delta S and thus a positive delta H, right? But then now going the other way, going from a gas to a liquid, that's a decrease in entropy. Correspondingly, that decrease in entropy will release heat into the surroundings, okay? So I'm going to move on from this because I think I could talk about this over and over and over and over again, and that might be best for a discussion, okay? So moving on. So heating at constant pressure. So, and I just said constant pressure for now, to make this a little more straightforward. But also, because if you think about it, when you're in the lab, And let's say you want to boil some water. You're heating it at constant pressure, right? This is what I'll say is ubiquitous. When we heat, we're almost always heating at constant pressure, okay? So let's put this together, okay? And let's start by reminding, I'll remind you that delta S, okay, from T initial to T final. So from initial to final, right, dq reversible over T initial, okay? Well, and I'm going to expand that now, and I'll say I know delta S, I can say is S T final minus S T initial, okay? And so now I'm going to start writing this as S T final equals S T initial. So I'm going to add the initial temperature over to the other side plus integrating from initial to final conditions of dq reversible divided by T. So what do we do with that dq reversible? Well, I will remind you that heat at constant pressure equals delta H, okay? And we also know, if I can keep going with this, I know that that also equals Cp times delta T, okay? Or, in other words, dH equals Cp dt. So just remember, heat delivered at constant pressure is called enthalpy, which is also the constant pressure heat capacity times dt, okay? So I'm going to rewrite this expression now as ST final equals ST initial plus, and then now, so I wrote TI-TF, that's technically not correct, right? It should be QI-QF, so I'll just write IF here. But now I can replace this whole expression with Cp dt divided by T integrated from Ti to Tf, okay? And now I haven't specified what my initial temperature and my Ti or Tf is, but if you look at this graph here, okay, so on this scale here, we've got Cp divided by T, or S, all right? And if you notice what happens when we start heating, we heat a solid. When it gets to that melting point, just as we described, right, like in this picture right here, there's a jump. That's the latent heat of that phase transition, okay? So what happens over that range? Can we use this whole equation? Well, as it turns out, no, we can't. We have to start expanding it, okay? And I'm going to expand it via the following. Now I'm going to say Sm, and I'm just going to start writing T, and I'm saying Sm to deal with molar entropy, equals Sm 0, okay? And then now I'm going to integrate this from 0 all the way to T. And here's how this is going to go, okay? When I start at 0 and I start integrating it all the way through, I'm going to first hit the freezing point. I have to stop right there. I can only integrate this first integral from 0 Kelvin to the freezing point. And the reason for that is because we know the heat capacity of the solid is going to be different than the heat capacity of the liquid, which will be different than the heat capacity of the gas. So in other words, now on this integral, I can write Cp, constant pressure, molar heat capacity of the solid, okay, divided by temperature times dt. And we know that that CPM as a function, that this equation, CPM, okay, I'll remind you, I'll just write it up here. CPM is a function of temperature, right? function of T. So you know from your working on your exam that we can supply a constant value into CPM, but a better approach would be to put an equation in there that is a function of temperature that will get integrated with respect to temperature. Okay? So now that's the heat capacity of the solid, dT. Okay. So now what happens as we keep increasing the temperature? Well, we have to pay the tax man for the phase transition. And that phase transition is melting. So that's going to be now plus delta H melt divided by T melt. Okay? And the reason why it's delta H divided by T is because, look, we're saying entropy equals all this stuff. We know that entropy is delta H divided by T. Okay? So now when I do this whole expression right here, the way this is written, this is only going to take me up to here and then to right here. Right? The integral took me up to this point, and then by just saying plus this latent heat, that takes me up to this stair step. Okay? Well, now I've got another phase to integrate over. And so now I can say plus, now I'm going to integrate this. I'm gonna use melt. I wrote F right here, but just so we're not confusing that with like final and initial, right? The F was supposed to be for fusion. I'm gonna write melt, T melt, like for the melting point, okay? Now we can integrate this from T melting point to T boiling point, right? So this goes now from TF to TB, or the melting temperature to the boiling temperature. And we know that now that's going to be Cp, molar heat capacity of the liquid divided by temperature, D temperature. Okay? Plus, we know that there's now going to be, as soon as I get to that boiling point, the integral gets me that far, but now I've got some latent heat that I have to deal with. Okay? So that's going to be plus delta H of vaporization, or I'll say delta H boil, divided by T boil. Okay? But that still doesn't take me up to this generic T, whatever that T might be. Suppose it's like somewhere right here, right? Somewhere, some gas phase temperature. Okay? So now what I need to do is integrate over the phase of the gas. And so now I can integrate this thing from T boil to just T, whatever my T might be, right? And now that's going to be the molar heat capacity of the gas phase divided by temperature, D temperature. And let's box all of that up, because this, little did you know, turned into a mess in a hurry. Okay, so let's back up and talk about this. If I want to calculate the entropy, so notice that this is no longer delta S. This is just S. So this is like saying, what is the molar entropy at a specified temperature? Okay. Well, it's going to equal the molar entropy at 0 Kelvin plus the integral from 0 Kelvin to the melting temperature of the solid phase, which now entropy, I know I put a whole bunch of different equations on here. Entropy is dQ divided by T, which is the same thing as saying that it's delta H divided by T, which is the same thing as saying that it's Cp over T dt. So Cp divided by T times dt integral gives you entropy. Okay, so now we've integrated over the solid phase. But once we pass that melting point, we have to pay the tax man. We have to add that latent heat, plus delta H melt divided by temperature. Okay, so now we get past the melting point. Now we're in a liquid. Now we can integrate from the melting point to the boiling point. Okay, and that, you know, would be the heat capacity of the liquid, Cp over T dt. Okay, plus delta H boil divided by T boil. So, right, if we go past the boiling point, we have to pay the latent heat of evaporation. And then now finally, if our temperature is, let's say, somewhere past the boiling point, then we integrate from T boil all the way to whatever that temperature is. Okay. Not a good idea to use constant values of heat capacity in these integrals because this is a really wide range of temperature, and over a wide range of temperature, heat capacity will vary. So we have to supply like an equation, a function of t, and integrate that function with respect to dt. But don't forget, this is a function of t, but then it also gets divided by t. Okay? So I just want to briefly show then, well, how do we calculate delta H, just as a quick comparison? Okay? So as a quick comparison, I can calculate my molar entropy by the following. I'll say it's some integral, and I'm just going to say from 0 to t of Cp over t dt. And so that it also includes the delta H of that situation divided by the temperature at which that happens. Okay? And then plus we know if there's phase transitions, right, there's more and more of these. Okay? Well, let's back up for a second. How do we just calculate the molar entropy? How do we get that? Well, we can actually follow this same procedure. 0 to t. But now how is it different? Well, remember, delta H equals Cp delta t. So now in this integral, instead of saying Cp divided by t dt, it's just Cp dt. And now instead of saying plus delta H divided by t, it's just plus delta H of that phase transition. Okay? So these are two really important equations that we're going to explore in more detail in the computer lab activity, like how we can actually calculate what the molar entropy at a certain value is. Okay? What is next? Yes, okay. And so again, I'll note that, right, HMT minus HM0 would give us delta H, and specifically if T was equal to 298, then that gives us the standard change in enthalpy. Or similarly, when we look at this, okay, and T is 298, we can call this delta S standard. I'll put M for the molarity, okay, standard. Now, what about this whole business of SM at 0, okay? What about that whole business? Well, that's what we call a third law entropy. And as it turns out, the third law of thermodynamics is really simple. The third law of thermodynamics says S equals 0 at T equals 0, right? It's as simple as that, okay? And this comes from the idea of the statistical definition of entropy, S equals KB natural log of W. And if we go into hideous detail with our molecular partition functions, we would find that W equals 1 when T equals 0. So there's only one state of the system at 0 Kelvin. And then, of course, when the natural log of 1 is 0, so this just gives us entropy equal to 0. Okay? Well, as it turns out, it's pretty difficult to actually measure this. It's extremely difficult to measure this. We have to get down to 0 Kelvin, right? That's really hard, okay? And so, for example, suppose you couldn't get down to 0 Kelvin. Suppose your measurement started at 78 Kelvin, which is liquid nitrogen temperature, okay? Your molar entropy, so this quantity, SM standard, and I'm not talking about delta. Let me back up here, and I'm going to write, when this is 298, I put delta molar, but I can also put that little standard notation symbol there, right? If you just want to know what is the molar entropy, the standard molar entropy, you have to be able to measure the molar entropy at 0 Kelvin. It's really difficult to do that, okay? And you're going to explore that more in the computer lab activity, all right? But what I do want to point out, like let's look at, I want to pick out just one of these values, or just, there's a whole mess of these values. And of course, the one that I want is not on here. Let's pick on methane, okay? I wanted to talk about nitrogen, but let's pick on methane. So we know the molar entropy of methane, the standard molar entropy, 186.3 joule per Kelvin per mole. Okay. Well, methane we know is a gas at 298 K. So to calculate this value for methane, we would have had to do this entire equation, right? That's kind of what I'm trying to show you, is we know that methane is a gas at 298 K. So to calculate that standard molar entropy of methane at 298 K, we would have to go through this whole gamut. But when we look at like these liquids, for example, benzene, right, to calculate that value, we wouldn't have to go through that whole situation, right? Because benzene is a liquid at 298 K, so we would not have included that gas contribution. So that's really kind of what I wanted to just point out with these third law of thermodynamics. When we talk about calculate a third law entropy, okay, what it means is we've been able to get our data down. So in our thermogram, we got our thermogram all the way down to 0 Kelvin, or damn close to it, to get a proper third law entropy. Okay? And the reason why the thermogram, because again, right, we don't have an entropy meter, but we do have a thermometer. And the thermometer allows us to calculate the heat capacity, or to measure the heat capacity. And so by measuring the heat capacity, these two equations, right? By measuring the heat capacity, we get the entropy and the enthalpy. So really, when you think about this, literally the only thing we measure in thermodynamics for these thermodynamic potentials, specifically enthalpy and entropy, is the temperature. All we need is a thermometer, and we can get the heat capacity and the entropy. Okay, and let's see here. That is all I wanted to say on this little short and sweet lecture. Okay, and I kind of left this stuff hanging because we're gonna explore more of these third law entropy calculations in the computer lab activities. Okay, I'll see you on the next video, folks.